Okay students, this is the final part of the videos for the problem 1. These are just a few general comments about the analysis and things that you should take note of. Alright, in this course we're only going to worry about Newton's second law and Newton's first and third law, where they are reaction forces. In the later part of your studies, if you get to the BTEC, you will use something called Lagrange's equations. Newton's law is basically mass times acceleration is the resultant force. Okay, let's just quickly write down that equation and understand what that means. Mass times acceleration is the resultant force. How do we apply that when we have a very complicated system that could be at angles and different inclinations? What do we do? Essentially, Newton's second law applies to components of displacements in a particular direction. What does that mean? That means you take a particular direction in your model. In this case, we assumed the deflection is x1 in that direction, and the deflection of the mass 2 is x2 in that particular direction. So essentially, Newton's law applies to components in spatial directions. So if you have a system of coordinates this is a right-hand system. A right-hand system means, a right-hand system means you take your hand, you take the cross product, and then that'll give you the direction of the other system. It is technically possible to use left-handed systems, but it gets a bit complicated. So if we have a three-dimensional system, we basically choose components, a Cartesian XYZ system, and then Newton's law will apply to components in the coordinate system. In other words, if we have a mass m and there are various forces acting on the system, for a particular point we would have three corresponding Newton's equations for each of the three components. In other words, we would have mass is equal to the force in the x's, mass in the y, if they are only linear forces. So in this particular problem, the mass m1 is specifically constrained to move in this direction only. So we would only have a corresponding Newton's equation for that particular direction. If there are three directions that the mass could move in, we would have three equations. An equivalent system that you would have to have is for the angles. Okay, so for a general point particle in space, there are three scalar equations for the x and y and z direction, and three corresponding angular equations, where theta 1, theta 2, and theta 3 are the different angles. So when you're solving more complicated problems, you have to look at what the constraints are. In this course, we won't really worry about the three-dimensional system. We'll only worry about single degree of freedom systems. When you get to the BTEC, you'll worry about what is called multiple degree of freedom systems. And then that is all I really need to say over here. So when you derive the equation at the end of the day, essentially you have an oscillation. The mass m1 moving in the x1 direction will go up or down, and the mass m2 moving in the vertical direction would go up or down, as the case may be. Remember that we had a relationship between A1 and A2 when we looked at the length of the strings. So if we solve the problem for x1, we've automatically solved it for the x2 direction as well. The equation of motion that we derived was in the general form: mass times the double derivative plus some spring constant times x is equal to 0. So that is an equation for mass spring in one dimension. This equation of motion, this particular equation, is known as a simple harmonic motion, SHM. So simple harmonic motion means it's basically an oscillation, and the oscillation would be for the mass m1 going up and down the incline and the mass m2 going up and down. Final comments: why did I disregard the gravity? It's a bit of a tricky question. The answer is you should look in your textbook, but essentially when we solve this systems in this course, we look at steady states. So technically there is a gravity, the gravity is pulling down, and it should be considered. But what we assume to keep things simple is that the system achieves a steady state, gravity pulls the string down, it stretches the spring and the ropes and so on and so forth, and everything gets to an equilibrium point. And then we only derive the equation of motion as it oscillates and moves about that equilibrium point. I'll make a comment in the website and then you can understand what it is. But to keep a long story short, we worry only about steady state and we usually disregard gravity unless we're trying to solve the entire system as the spring stretches and compresses and moves back and forth. Usually that's a bit too complicated and we won't worry about it in this course. Okay students, that's the end of the videos for problem 1. Thank you.